Welcome back to another exercise. As I mentioned in the previous video, we're going to start with a series of examples about trains that move in different directions, that they move from one city to another, that they encounter, they will pass each other, or they chase each other. These are, as I mentioned, some sort of classic types of problems in kinematics. So let's dive in. A train travels from city A to city B at 85 kilometers per hour. Whereas another train travels from city B to city A at 95 kilometers per hour. If the two cities are 400 kilometers apart, find when and how far from city A the two trains will pass each other if they depart at the same time. Alright, so here we have a lot of information in only these 2.5 lines. So let's start by noticing that we are given the speed of each train. So here we have the speed of the first train is 85 kilometers per hour. We're also given the speed of the second train, 95 kilometers per hour. We also know that it's traveling in the opposite direction. Finally, we have the distance between the two cities. So this is how far apart they start. The two trains will start their motion, we're told, at the same time, but 400 kilometers apart from one another. This is all we know from the problem. The next step is always make a little cartoon, draw the situation. So for this, the step number 1 is select coordinates. As usual, in this kind of problem, we only have the x-axis because we only have one dimension. The motion only occurs in one dimension. So this arrow here will denote our x-axis, as usual, from left to right. So quantities to the right will be positive, quantities to the left will be negative. Let's draw somewhere here the coordinate x equals 0, and let's put here city A, and somewhere here at some distance, let's call it uppercase D, is city B. We know that there are two trains. One, let me use a different color. So the first train is moving from left to right with some speed that we can just call it V1. So this will be train number 1. For train number 2, I use another color. This train is going from B to A to the left. Some speed V2. Of course, we know that these trains will meet somewhere, so they will pass each other somewhere. We don't know where. Let's just put it here, and let's call that distance D. So the coordinate will be D measured from 0, which is the location of city A. And that's it. That's our cartoon. That is the situation, and now we can start writing equations. In previous examples, we only had one equation because we only had one object. Now we have two trains, so we have two objects that are moving, so we're going to have one equation for each train. So let's start here with train 1, and the equation of motion is x, I will call it x1, will be x1 0, that is the initial coordinate of train number 1, times v1 times t1. So notice that we add the little 1, the subscript 1 everywhere, because this means this is the equation valid for the first train. The initial coordinate of train number 1 is city A, so it's 0. So this is, again, was just a choice, so we set that term to 0. We can forget about that. So x1 will simplify to v1 times t1. Let's now look at train 2. For train 2, we have exactly the same equation, but we add a subscript 2 everywhere. So this will be x2 0, that is the initial coordinate of train 2, v2 times t2. Now we cannot set this term to 0. We did that with the first train, but we cannot do that with the second train, because the second train started from city B, which is located at some distance, uppercase D. So the initial coordinate is D. plus v2 times t2. So this is the equation for the position of the second train. And there we have it, two equations, two trains. Now we need to see what happened at the passing point. So we know that the two trains will meet somewhere here. We call this distance little d. We don't know where that is in fact the question. So we can call this the meeting point. Meeting point. That is our meeting point. We don't know what that is. We don't know when that happens, and that is in fact the question. Notice we have two questions. We're going to get back to that in a second. So here we're going to write now the condition for this meeting point. So at meeting point, we need to set two conditions. The first condition is we want the two trains to be at this point. That's the idea. That is the meaning of the two trains passing each other. So we want the coordinate of the first train to be equal to the coordinate of the second train, and we call this quantity d, little d. Okay, we don't know what this is, doesn't matter, just call it d for now. The other condition is, since the two trains started at the same time, the meeting condition requires that the time for the two trains is the same. Otherwise, they will not meet. That is a condition of meeting. They have to be the same coordinate in space and in time. In other words, we want t1 to be the same as t2, and we can give it a simple name, just call it t, just to simplify the notation. So this is the condition of the two trains meeting at point D. In other words, the two trains passing each other. So I can take the equation for the first train, take the equation for the second train, and impose this condition. So let's do that. For the first train, we have x1, which is now d, is the same as v1 times t1, which we simply call t. So we simply drop the subscript 1. For the second train, we also x2 will be also d, and it's equal to uppercase D plus v2 times t2, which we now call t. So here we have imposed this condition, and this is important. We're going to do this in many of the following problems. Okay, so we have imposed the condition of the two trains passing each other at the meeting point. We have two unknowns, which is little d and t. We have two unknowns, two equations, so we should be able to solve this problem. How is this solved? Well, in these two equations, we have that the left-hand side is d, so therefore they're the same. That means that the right-hand side of each of these two equations must also be the same. In other words, I can write v1 times t, which is the right-hand side of the first equation, must be equal to the right-hand side of the second equation, d plus v2t. And here is just algebra. I have a linear equation for t. Notice that the little d disappeared, so we have only one unknown, therefore we can solve it. So now it's just algebra manipulation here. We pass this term, the terms with the t, I want to collect them all together, so I will pass that term to the left. v2t equal big D. Now I can take the common factor t and write this as t times v1 minus v2. Just a simple factorization. And now I pass this to the other side of the equation. In other words, I divide the two sides of the equation by this term. So t becomes d divided by v1 minus v2. And there we have an expression for the time. And now we can plug the numbers. So d, we know, is 400 kilometers, because that is how far apart the two cities are. v1 is the speed of the first train, 85 kilometers per hour, minus, and here I'm going to use a parenthesis because we have to be careful. The second train, as shown in the cartoon here, is moving from right to left. That means that its velocity is pointing to the negative side of x. So x Our choice was that x will be pointing from left to right, so everything to the right will be positive, anything to the left will be negative. In other words, v2, this 95 kilometers per hour that we're given, is the speed, but we have to put an extra minus here because the velocity will be negative. So it's minus 95 kilometers per hour. So just to repeat that, the first minus here comes just from solving this set of equations, but the second minus inside the parentheses comes from the fact that the second train is moving from right to left. That is an arrow pointing to the left, therefore, since our x-axis points to the right, that means it should have an extra minus. So once that is clear, we can plug the numbers. And we go to the calculator. We have 400 divided by parentheses. Have to be careful here. Is 85 minus minus, so this is the same as plus 95. Close parentheses. We get 2.2. So this is 2.2. And if we pay attention to the units, we have kilometers divided by kilometers per hour. So just as in previous problems, we get the right units. This will be hours. So this is the time. Time is 2.2 hours. So that is the answer to the first part. We are being asked two questions here. We're asked to find the when, that means time, and how far from city A, that is where. So we already have the when. We need to find the how far from city A. Given the lack space, I will just continue. I will just put a line here, and I will do the second part here. This is very straightforward now because we know the time of the motion, and we can take any of the two equations from here. The first or the second equation, they both will give us the same answer. So let's pick the first one because it's easier. The first equation says D is V1T. V1 we know is 85 kilometers per hour times T, which we just found, is 2.2 hours. So once again, since we're using all units, the length is always in kilometers. Everything cancels properly. The time cancels here. It's hours with the other hours. We're going to get an answer in kilometers. Let's see how much. So we have 85 times 2.2, 187. So we write here 187 kilometers. And that is little d. This is little d. So we have found the distance from A, from city A, of the meeting point, which is exactly what we're being asked to find.